In previous chapters, you learned that gapless systems can be topological too. And the entire topology is encapsulated in band touching points. These could be lines or points in reciprocal space. We are going to focus on Weyl points. These are a point touching of two bands that are otherwise non-degenerate. And we are going to think about the simplest case scenario for now, in which you have only two Weyl points. A Weyl point is topological because it emits Berry curvature or absorbs it. Namely, if you write down the Hamiltonian that represents the low energy expansion around the Weyl point, and you calculate the Berry curvature, it will have a monopole form, looking like this. Then if you think about the chemical potential being very close to the Weyl point, then the Fermi surface will basically be a sphere encapsulating the Weyl point. And you can calculate the integral over the entire Fermi surface, which is a closed manifold. And that integral, by Gauss's theorem, will essentially count the number of monopoles inside of it. So we can define a topological quantum number called the chirality, defined like this, up to a sign very similar to the definition of the Chern number that you already know. And this will be the topological charge in our system. And now that you know that gapless systems can be topological too, you can ask yourself what happens when the system is finite? What happens when you introduce a surface? And can those topological systems support robust surface states? And if so, what is their nature? So let's think about a three-dimensional system like this, where the separation between two Weyl points that are two oppositely charged monopoles, the separation between them is represented by a vector, and that vector is aligned with one of the momentum direction. Let's say it's kz. And then this will be kx, and this will be ky. Okay? So let's consider what happens when that vector has a projection on one of the surfaces. We know that the surface is the place where the system has to become trivial, because outside of the system we encounter the vacuum, which is topologically trivial. So the surface basically represents the point of annihilation of the Weyl points. And the question whether that vector has a finite projection on the surface or not determines whether the Weyl points have to trace a line in order to meet and annihilate with one another. If we look at a surface, for example, on which the vector doesn't have a projection, then the Weyl points basically project onto one another and they gap instantly. This is not true for surfaces that have a finite projection. There you can trace the annihilation course of the two Weyl points. This will essentially be a line of states, as we will argue in a minute, and these states carry chiral currents. They have a name. They are called Fermi arcs. The reason they are called Fermi arcs is because they are open contours. They begin at the projection of one Weyl point and terminate near the other. This is, of course, also correct for the bottom surface here. It also has two projections of the Weyl points that have a finite separation between them, and therefore this surface will also host a Fermi arc. This is a view from the top of the system. From the top of the system, you can see that the two arcs encapsulate a finite Fermi surface, but you have to be careful because one of them is an open arc on the top surface and the other is an open arc on the bottom surface. So there are many ways to understand Weyl points and Fermi arcs. And usually people say that the Fermi arcs is a bit like the Dirac string that connects two topological objects, the two topological monopoles. But we want to look at it from a slightly more formal perspective and try to connect the existence of Fermi arcs to that of Chern insulators in two dimensions. And we're going to do this by considering a simple two-band model. Okay, so let's consider the simple two-band model that I'm showing here. In this simple two-band model, and you can see the band structure here on top, there are two Weyl points. These Weyl points are separated along the kz direction. So you can consider this three-dimensional model, but you can also look at it a little bit differently. Namely, you can think about it as a stack of two-dimensional models. Let's freeze the kz coordinate and consider it a parameter of the model. For each kz, what we essentially have is a two-band model which is two-dimensional and has a finite gap. This is true as long as kz doesn't coincide with a band touching point. The size of the gap is not really important. What's essential is that it's there, because if you have a two-dimensional model and that model has a gap, then you can calculate the Chern number on that plane, and it will give you some integer value. Okay? Whether that value is 0 or non-zero remains to be seen. But you can certainly define it. Remember that the two perpendicular momentum directions are also periodic, so this would be a closed manifold. Okay, so let's envision why that plane might have a non-zero Chern number. So for this particular model, for example, if you draw a plane between these two monopoles, then that plane will be threaded by a finite flux, because on one side of it you have a monopole emitting Berry curvature, and on the other side of it you have a monopole absorbing it. So you can integrate the Berry curvature over that plane and you will get some finite value, and that finite value will reflect the number of monopoles to the right or to the left. This doesn't have to be the case. This is specifically true for this model. There could be other models or situations in which you will get a non-trivial Chern number outside, namely on planes that connect to one another through the ends of the Brillouin zone, which is of course periodic. But the point is that there is always a finite segment of kz, or a finite range of kz's, in which these stacks represent non-trivial Chern insulators. And therefore, if we have Chern insulators and we make the system finite, then we know that we must have surface states. And those surface states will be chiral, and they will propagate and be bound to the surface plane. If you draw the band structure on an open slab, of course the cones will not be continuous, they will be discretized, but this is just to make the point that the Fermi arc will appear somewhere connecting these two points. So if we determine that the Weyl points are separated along kz, and this is the kx direction, and this is the ky direction, then if I look at the Fermi surface on the surface, it will be a contour extending from one kz to another. If I draw the dispersion on the surface, then as a function of kx, it will just be represented by this chiral mode. And of course, a similar thing happens at the bottom surface, where I have a mode of opposite chirality, of course intersecting at 0. Okay, so we argued that Weyl semimetals have to support surface states. And we argued that those surface states are open Fermi arcs. And now you might ask yourself, what happens when you have more than 2 Weyl points? Let's say I have 4, for example. Let's say it's a time reversal invariant system, and each Weyl point is accompanied by time reversed partners of the same chirality. So we have 2 pairs of Weyl points, and as you might have guessed, since arcs have to connect points of positive chirality or projections of points of positive chirality to those of negative chiralities, there is not only one way to connect them. So this would be one way. Both of these arcs appear on the top surface right now, and not one on the top and one on the bottom. There is another pair on the bottom surface. But there is also another way to connect, which is this way. Both ways are valid, namely, the chirality can be either of those, and this is a non-universal property of the system. And in fact, even within a single system, you could end up with a situation in which a different lattice termination will result in a rewiring of this picture and a change in the connectivity of the Fermi arcs. But the point is that they have to be there. There has to be a pair of them. And in this case, the chiral current will flow in opposite directions, not in the top and in the bottom surface, but on the same surface, just contributed by 2 Fermi arcs. So to summarize, I told you that topological semimetals host surface states, and these surface states are arcs, namely open contours that begin and terminate at the projections of the Weyl points onto the surface. Each arc will contribute chiral currents. These are bound to the surface of the system, and the symmetries will determine if the chirality is compensated for within a single surface or between surfaces. And finally, the arc connectivity may vary. If you have several Weyl points in your system and you have several projections of those onto the surface, then the details of the system will determine the arc connectivity. But the fact that the arcs have to be there for systems that have a finite projection of Weyl node separations, that is a topological fact.